Right, so let's find end behavior of rational functions. So in calculus talk, when we want to find end behavior, we write things generally this way. What happens as x approaches infinity to our function, and it could equal some number. Now, this value val could be a number. It could be like infinite. I mean, there's times where maybe something else kind of weird is going on, where it doesn't end up equaling anything. So kind of things to kind of note here. I kind of said in the polynomial part, but this below is a statement about the domain of the function. What are our values of x doing? And this is a statement about our range. What are our y values doing? If they approach some number, we say that it kind of equals L, where L would be the limit of the function. Right. So when we think about rational functions, the nice thing is that we're always going to know what's going to happen. We're either going to approach positive or negative infinity. We're going to approach some number. And many times it's going to also equal zero. It's going to be just a stretch number. I would recommend that we understand conceptually what's going on here, as opposed to just kind of memorizing what happens in each of these cases. So just in case we do want to just like memorize what happens in these cases, whenever the degree of the top is larger than the degree of the bottom, the horizontal asymptote is going to be infinite, either a positive or negative infinity, but it's going to be one of the two infinities. Now, I care about why. All right, so let's see. So when we think about what happens, I'm actually going to do this bottom one first. I think it's a little bit easier to understand. So if I look at this function as x gets really, 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 really big, right? So what does this approach? So let's think of a really, really big number. When I ask students like, hey, what's a big number? They're always like 100, right? So let's think about like 100 billion, trillion, quadrillions, right? Some stupidly large number. So to make it a little bit easier, just because 100 billion quadrillion is probably something that you can't visualize, let's just think about it as a million. So imagine you had $1 million right now. So let's pretend that x equals 1 million. So if I plug in a million to the bottom, think about you have $1 million and I ask you for $3, right? You're going to lose $3. Are you really worried about the $3 that you're about to lose? Well, probably not, right? You're a millionaire, right? $3, whatever. So long term, this x minus 3 really starts acting like just x, right? So if you have $3 less than a million, you still basically have $1 million, right? You're not really feeling that loss of 3. So same idea up here, if you have a million to the third power, right? This is a huge number, right? If I take a million and raise it to the third power, I'm going to have 1 and then 18 zeros at the end of it. And so that'd be a good day in the old bank account. So if you have 1 and 18 zeros at the end of it, and I ask you for $9, again, you're not really feeling that $9, right? It's like nothing to you. If you have $5 million compared to one with 18 zeros at the end of it, that $5 million isn't putting a dent in your bank account. So long term, the only thing that really affects this function is going to be this first term, this highest degree value, x to the third power. So if I simplify this, x cubed over x, this would give me x squared. So the idea is that this function here eventually starts acting like this function here. Let me actually do this. It's not the limit, right? So this function here eventually starts acting like this function here. It starts acting like a regular old quadratic. So a whole bunch of crazy things in between, but eventually it has to start acting like x squared. And we know what x squared looks like. We know x squared just simply does this as its end behavior. So as x goes off towards infinity, x squared is also approaching infinity. So this kind of weird function should also go off towards infinity. So here, if x approached negative infinity, as we got bigger in the negative direction, our function should also approach infinity. So this is why in terms of this, what I have to do with negative. So this is why whenever the top has a larger degree than the bottom, we're going to get an infinity. Could be a positive, could be a negative, right? But it's going to approach some type of infinity. So if I look at kind of like this second one, oh, let me actually just show you this, right? So suppose I just threw this into Desmos for a second. So I got x to the third power. Oops. X to the third power plus 5x plus 9. And if I take this thing and I divide by x minus 3, right? So we kind of like do some weird stuff. We kind of have some weird stuff kind of going on here, right? There's some vertical asymptote. So this is what this function kind of looks like. But if I zoom out enough, maybe even zoom out a little bit more. If I zoom out enough and I just show you that picture, this looks exactly like a quadratic. And we're not even on like the million scale, right? This is looking like a quadratic. This is like 1,000, a negative 1,000, right? So long term, of course, this thing's going to look like a quadratic, right? That's what this is saying, or that's what this kind of like end behavior is saying for us. So if I look at the opposite case of this, right? So suppose suppose the degree of the bottom is bigger than the degree of the top. We're going to have horizontal asymptote of like y equals 0, aka the x-axis, by kind of the same argument, right? So if x is like 1,000,000 here, if I have 1,000,000 to the 5th power, and you lose $3, like $3 is nothing. So eventually this bottom starts acting like x to the 5th. And once again, this top starts acting like just the highest power term, x squared. So eventually this starts acting like 1 over x cubed. So if I thought about, hey, what happens? What's the limits of 1 over x cubed? Well, let's think about what 1 over like 1,000,000 cubed is going to be. It's going to be tiny, right? So you have one cookie and 1,000,000 cubed friends come over. How much parts of that cookie is everybody getting? Like nothing, a minuscule, a fraction, some like atom of it. So this thing starts acting like 0. Same logic. This is going to act like 1 over x cubed. And so as x goes off towards negative infinity, it's still going to approach 0, right? So except from the like negative direction. So if I kind of showed you this as a graph, if I had an x squared, I think I just got lazy and just squared this thing instead, over x to the 5th power. That's not x to the 5th power. That's not x to the 5th power. No, I just broke it. X raised to the 5th power. There we go. Let me get rid of that 2. This was the function. Yeah, that's the function. All right, so if I look at this function again, kind of like short term, it's doing like a whole bunch of funky stuff around the origin. But if I just zoom out a bunch, well, this thing starts acting like 0, right? So long-term behavior looks like I adjust the x-axis, just that line. And then finally, if the degree of the top is the same as the bottom, a horizontal asymptote is going to be y equals the lead coefficient of the top. Sometimes called the numerator, more commonly called the numerator, divided by the lead coefficient of the denominator. And same kind of logic here, right? If x is some stupidly large number, if x is like 1,000,000, again, like this -3 isn't really going to affect things. None of these things are going to affect stuff. So eventually we're going to start acting like 5x squared over 8x squared. Those x squareds cancel, and we start acting like 5/8, right? It's that ratio of the top leading coefficient to the bottom coefficient. And nothing kind of changes here, right? All those things kind of go away. And again, we're kind of acting like 5x squared over 8x squared, which is going to be 5/8. So you could probably just imagine in Desmos, we're going to get the same thing except as a previous one, except up 5/8 of a unit.